Okay, so a little bit of help for exercise 381. First of all, you can see here that you've got concentration against rate, and you should remember that if you were to plot a concentration down here against rate along here, rate, you've got a few types of graphs. So if it's zero order, first order, second order, you should remember the kind of shapes of the graphs. So that's the idea behind what you do with this data. Following on from that, in terms of the rate law, the value of x here is the order of reaction with respect to N2O5. That's going to be dependent on the shape of the graph, and I won't go into details on that one, but you've got that in your notes. And last point, what is the value of K at 45 degrees? If you have a look here, the reaction is at 45 degrees. If you've got rates and you've got concentration of N2O5, depending on what you found was X here, you can substitute rate, concentration of N2O5, X in there, and that will leave you the opportunity to work out X. The last bit, C, it can be calculated from the figures given that. So this is working out the concentration going from 2 times 10 to the minus 2 to 1 times 10 to the minus 2. That's looking at how that turns to half its value here. And you've got the half-life as being 1,386 seconds. I have a sneaky suspicion I can guess what this is. And bearing in mind this, I'm being a bit cryptic here, that's going to link in with this. So think about first order reactions, zero order reactions, second order reactions, and how half-life changes with those. Last point here is it's saying that 2 molecules of N2O5 react to produce 3 gaseous molecules. So 2 here produces 2 plus 1, which is 3 molecules. So given that, essentially what's the measurable change as a reaction proceeds from left to right? You should work out there's a measurable change. Bearing in mind that measurable change, you should be able to work out a simple apparatus that you could use to calculate the rate of reaction. Okay, good luck with that.